Hello everyone in Beijing and everywhere, and many thanks to the organizers of this workshop for bringing us together over time and space through this session. I am presenting here also on behalf of Nitzan Gado, who wrote the code for this project. This work started in fact as a course assignment just before our master graduation at the Hebrew University, and I thank Yuval Feinstein, who taught that course, for bringing us together. What do we mean by feeding a gazetteer? In order to serve as a gazetteer, especially in its digital functionality, and we elaborate on this in the written paper, we need as many variant names for each place that will be linked to it. One obvious way would be to digitize print gazetteers. Another would be to assemble born digital resources. In creating Kima, our Gazetteer for Hebrew script place names, we found a treasure of variant names in library catalogs. In a Mark 21 catalog entry, the original historical place name that appears on the title page is documented along with a normalized name. Another method for populating Gazetteer is the annotation and linking of place names in sources. As long as you add them then to your Gazetteer, to add the variant forms that were not previously detected there. The two latter methods have the advantage of providing dated attestations of variants, and these make it possible to narrate and visualize the political, cultural, and linguistic history of the naming of places. Here, we see the examples of Amsterdam, Frankfurt am Main, and Salonika with their varied attested Hebrew toponyms as they are visualized on the Kima website. The combination of all these methods I mentioned before yielded so far over 120,000 variant toponyms in our Gazetteer. While this may sound like a lot, it is far from sufficient to represent the richness and diversity of place naming in the history of Hebrew languages. In order to make a Gazetteer more effective in retrieving toponyms and extracting them from text, we need more variants. Before proceeding to tell you what we did in order to get them, let me first introduce our corpus. We would not have had this treasure of a Hebrew historical toponym-rich corpus if it were not for this immense digitization project by Tel Aviv University and the National Library of Israel, JPRIS. The website provides browsing and search functionality to Jewish newspapers in various languages from around the world and over many decades. In itself, however, this is not enough to make it into a research corpus. For this purpose, JPRIS collaborated with a team at OmiLab of the Israeli Open University to create a pipeline that would improve OCR for 19th century Hebrew while keeping the valuable structural analysis of the newspapers. A balanced corpus of a 10-year span of 5 Hebrew newspapers was then made available in GitHub. In the work that we show here, also made available on GitHub, we used a less balanced but temporarily expanded corpus of these same 5 newspapers. As you can see, in the 19th century, Hebrew was mostly a European language. The newspapers, the leading Hebrew newspapers of the time, were published in multiple places in Jerusalem, but throughout Europe. We can therefore expect our corpus to have a good toponym coverage of at least the European sphere. So how do we proceed from here in order to mine toponyms from this corpus for our Gazetteer? We propose in our paper a workflow that leverages word embeddings. After cleaning the corpus, removing non-Hebrew characters, punctuation, numbers, also articles shorter than 20 words, we remain with 68,000 articles. We then use Gensim Word2Vec in order to create an embedding spaces for this corpus. In the embedding space, vectors represent for us the semantic of words. We expect words with a similar meaning or words that appear in similar contexts to be closer to one another in the latent space than non-related words. Hence, we expect that vectors for toponyms would be similar, closer to vectors of other toponyms. So we assembled a set of 1,000 unambiguous 19th century Hebrew toponyms, and used the model to extract the words with topmost of vector similarity to the words in this seed. Here on the left, you see the head of our seed list. The broad table is what our results look like. For each seed token, we get a count of its appearances in the corpus, its representation as a vector, and then a token which was found to be similar, again, a count of its appearances, its vector, and the degree of similarity between the two. Indeed, most of the similar tokens are themselves toponyms. Some of them we already knew. Some are previously unknown variant names of places which we already knew. And some are even new names for places which we did not know, meaning we did not previously have a record for them in our Gazetteer. We actually discovered new places with this method for our Gazetteer. The power of the method is undeniable, but we still needed to find a way to both assess and enhance the productivity and precision of our results. For this purpose, we annotated a test set from the 20 most similar words for our seed words and experimented with it. Here in the bottom left, you see our annotated set, colored red for false negatives and green for true ones, real toponyms. True toponyms we see appear between 1 and 45 times in the results. False non-toponym tokens appear only less than 12 times. So if we wish to start adding the results to our Gazetteer, we should proceed at the top with the terms that recur most often in our results. Moreover, we can see in the tree visualization up here, selecting only the terms that appear more than 3 or better yet more than 9 times in the results yields subset with much better accuracy levels. This can be seen in the rightmost branch. We get to 98.6% accuracy. Another helpful visualization was done using Gephi. We used the vector similarity pairs. We modeled them as connected knots. While the center of the circle is made of close-knit web of toponyms, the peripheral ring is made of many small separate clusters. Many of those consist of ambiguous terms which yield non-toponymic terms as targets. Those false non-toponymic results would only appear once as a result. Filtering out those isolated clusters would be another way we could refine this method. To summarize, we found that the most helpful parameter to ensure the accuracy of result was not the degree of similarity, nor the number of times the tokens appear in the corpus, but rather the number of times it was found as vector similar to source toponym in a list of the seed toponyms. This was found to be a much better parameter than corpus frequency and much better than the degree of similarity. One question may have bothered you all along. If we wanted to extract toponyms from a corpus, why not use NER, named entity recognition software? The short answer is that our next step would be to compare our method with NER, especially now that we have a new shiny NER software for Hebrew, NEMO. We plan to examine scenarios of combination between the two and the option of integrating them in a pipeline. To the longer answer, however, we give that in the paper. We add issues such as the morphological complexity of Hebrew, the lack of vowel letters that enhances disambiguity of words, the fact that existing tools were trained on contemporary rather than historical Hebrew, and the limited success of the tool with out-of-lexicon words. But we are going to try it. And apart from experimenting with NER, we also plan to try our method on languages in other corpora. We do not have a doubt about its success. Our curiosity is rather how useful this method would be in relation to named entity extraction tools in each of these languages. A reviewer of a paper also suggested to look into the applicability of the proposed method to other non-spatial domains. Motivated by her or his question, we tested small seeds of 5 terms each, representing emotions, positive and negative emotions in separate groups, names of famous personalities, ideology-related concept, and temporal terminology. In similar ways to our experience with toponym mining, we found vector similarity to be a useful discovery tool that we can use in order to reconstruct historical vocabularies of different sorts. It did not only get us words from the same domain, it succeeded in surprising us with historical, almost obsolete terms and forms that we would never have thought about ourselves. Just as a rich gazetteer is required in order to spatially explore a historical corpus, when approaching text with other research questions that call for text analysis, it is crucial to formulate your question in a language that is adapted to the language of the historical subject. Vector similarity and the workflow we suggested here for improving the accuracy of its results can be a valuable tool for reconstructing such historical vocabularies. Thank you, and we welcome any questions or comments that you may have.